This video is Mercury Tectonics Mapping Part 2. In this video, we're going to more specifically look at normal faults and the environments that they form in on Mercury. So Mercury is kind of a special planet in that we mostly see normal faults inside of impact craters. And again, impact craters, like you saw in the first part of the video, are really useful places for looking at tectonics and faults because we know what should have been there before. We know what the pre-existing surface would have looked like. So we're going to look at this MDIS. When I say MDIS, it's MDIS. This MDIS image of Mozart crater, or the western half of, or eastern half of Mozart crater. Mozart crater is a multi-ring basin. So here's the outside of that impact crater rim, and then inside we've got the second ring. I've got some of it popping up over here, and then we've got an older terrain around it. And the inside of this basin has been smoothed by volcanic infilling. So this smooth surface is kind of like flood volcanism surface. And we've got a little bit of smooth surface even outside of the crater. These stripes are ejecta. So if you see some lineation in the topography, that's what that is. And you might also see some changes in the topography where all of a sudden you have some smoothness that's kind of blocked out. Like over here, this area looks really smooth. This area looks really smooth. That's just an effect, a data effect or a data artifact. We also have two other data sources for this crater for you to work with. There's topography, so we can see white is the highest, then brown, then red. Okay, so we've got a lower topography area inside of the crater, higher topography outside the rim, just like we would expect. And then it kind of goes back downhill, maybe because there's other impacts over here. And this smoothed area is a little bit lower elevation. And then we have a true color enhanced image of the same area where you can see that interior ring is kind of bright. You can see the outer ring. And then you can see all of these younger, fresh impacts kind of standing out. So the rims are really what stand out here, are the rings and the young impacts. Okay, so let's go ahead and start defining units, and then we will talk about the tectonics within those units. So we've got some high topography areas out here that are really rough with some impacts over the top, but it's not heavily impacted, but it is rough terrain and high elevation. We've got a high elevation smooth terrain, and then we've got a low elevation smooth terrain, and we've got a secondary rim material. So let's sort out the observations versus interpretations in that. So remember, for your description, you're going to start with an observation or multiple observations, and then if you want, you follow it up with an interpretation. The data types that we are using for this are going to be the MDIS black and white image. We're going to use topography, which is a USGS overlay on top of the MDIS, and we're going to use enhanced true color. And we're going to use that for as many of those three data types for as many of these units as we can. So I like to start outside of the impact crater and work my way forward through time. So I'm going to start with unit 1 as being rough high topography. Okay, so we classified this as being rough topography. Rough, it's high, it's got lineations, streaking across it. It's not heavily cratered. We also had a second unit in high topography. I'm going to call it smooth high. So this unit was smoother, it was high elevation. Let's see, like no superposing craters, maybe one or two. So a few superposing craters. Anything else to be gained from this? No. I'm going to interpret that to be volcanic fill exterior to the crater. And that's not unusual. Like, the way that these things get filled in, or the way that flood volcanism happens, it's not because the impact has like punched a hole through the surface of a planet. It's that when that impact happens, an impact doesn't just make a hole, right? It makes this huge connected network of fractures. Okay. There's our rim. And let's say we have a central peak. Not to scale at all. We have this really interconnected fracture network, and so materials can make their way up and through those fractures, and as they come toward the surface, you can experience decompression, melting, because think too, like all of a sudden this whole weight of material that was once on top of these rocks, that's now gone. So maybe we have some decompression, melting. If there is going to be any magma that's down here, like let's make ourselves, let's Bob Ross it, make ourselves a happy little magma chamber. If we do have magma below the surface, that magma is going to try and find those pathways to make it to the surface, and it's going to utilize this fracture network to get up there and fill in that impact crater. So again, we're not punching a hole, we're making pathways. So we get that magma to the surface, we fill it in, and this is what we see. So it's not unusual to be loved by anyone. Okay, so if we have a fracture that comes to the surface, it's not crazy that that magma might migrate along that pathway, make it up there, and fill in some low areas outside of the impact crater. Okay, so we have volcanic fill exterior to the impact crater. Related to that, let's do smooth low. We're going to have smooth low topography. With a few superposing craters. Interior to Mozart crater. And we can interpret that to be volcanic fill. And then the fourth unit is going to be the peak ring unit. And yes, that is an interpretation, but I think it's a pretty sound interpretation based on the size of the impact crater. It's a pretty large crater. So, high topography, circular or bullseye in shape. In impact crater, and it's rocky or rough, interpreted to be peak ring material. All right, so let's take a look at our tectonics, because after all, the goal is to map structure. So here, these little linear features are the structures that we're actually looking at. These are the structures that we care about. Okay, so I'm going to zoom in just a little bit. Sorry if the camera wiggles. All right, does everybody see these little lines that are in here? Okay. Anybody else ever bake the top of a cheesecake that cracked? It's pretty frustrating. Okay, so these are negative topography features. So if you're seeing them as high elevation, just focus in on an impact crater, and then hopefully that will reorient your eye. So for example, this little line right here should be a little negative topography, so almost like a little trough. Same thing with these over here. All right, so if I were going to look along a line through here, let's go to our topography map for a second. If I were going to, for example, go from A to A prime, I would go across one of these little troughs. And this would be what I would see. Okay, sorry for the big reveal there real quick. Okay, so we would have low topography drop down in the middle of two blocks that are a little bit higher on the side. Because we have this low topography drop down, we can interpret this to be a normal fault or a graben system. Sorry. Get this over here just a little bit bigger. I'm not going to draw the whole thing, I'm just going to draw a cross section of this so you guys can see it. So we've got a hanging wall moved down relative to footwall sides that have moved up. And then to bring this into 3D, if you need it, it's like that. All right, so let's go back over here. Let's talk about how we would map these. So since we have grabens or normal faults in low topography, they've dropped down. They've probably cooled because of, or they've probably formed because of cooling and cracking on the surface. So if you've seen like mud dry up, these bits of rock kind of raft, they cool quickly and they pull apart to themselves. And the reason for that is that things exposed to space cool first. Things exposed to space cool first. So the top layer of this impact crater, as it flooded, that area cooled, and then below the surface it took more time to cool, and that surface just cracked and widened and opened up. All right, so let's talk about how we create this map across the whole surface. All right, so if I were going to map one of these features, first you have to decide if you have enough resolution to map both sides of that graben. So back to this drawing. Here, this side of the graben is a normal fault. And this opposite side of the graben that you can't see, this is also a normal fault. So for every graben, there's two normal faults. So if you're looking down on your map and the scale of your map is such that you can see both walls, say that's your drop down area and you can see both sides, then by all means, go ahead, map both sides, because both of those are faults. But if the scale of your map is closer to this, you're going to struggle a little bit more to map both those sides. You might even get to the point that the symbology you're using or your pen to mark this out is getting those walls closer and closer together, until, if we're really zoomed out, you can see how if this is what we're mapping at, one stroke of my pen is going to cover that whole area. So here, given the resolution we're mapping at, we're not going to map both sides of these features. We're just going to map the outlines of the features themselves. If there's an area you think you see one, you can go ahead and dash that in if you're not sure. I'm using blue to do these just so that when I go to put my units in, my unit boundaries will certainly be a different color than these. I have a couple papers published on mapping on Mercury, so if you think I'm doing this really fast and it freaks you out, just remember I got some experience doing it. Okay, let's write our units in, or our structure in, on our map key. The structures are normal faults, or graben. And our description of this is going to be low topography. They're interconnected. They kind of, oh, forgot some here. They kind of make a polygon type pattern. They are located within the peak ring. And they're all relatively short. No one of them is dominating. So I'm going to say relatively uniform length distribution. I'm using all the data to do that. Now, really, if we did a length study where we zoomed in, we would probably find that they have a logarithmic distribution. Most faults do. But at the scale we mapped at, everything seems to be about the same length. There's no one fault that's dominating this map. So let's put our other units in. Okay, high rough topography is going to be out here. Again, if you're not sure, just dash. Okay, so it's all this outer area. I don't know anything that's going on out here. All right, so I'm going to color this one in yellow. If at any point you're coloring and you're like, oh no, I'm coloring on something smooth, stop. It's okay to identify units after you've already started mapping, and maybe you need to go back and revise your map. Map revision is your friend, not your enemy. It'll give you a better product in the end. Okay, like right in here, that's a rocky unit. That's not smooth. So I need to isolate that. It's also okay for you to do this differently from me. Okay. All right. Get that a little bit darker yellow. All right, now let's get those units that are smooth and high topography. Let's do the peak ring unit. I'm just surrounding most of it. I'm not worried about being super precise on this. If you want to dash in that back boundary, that's up to you. That's totally fine. Some of you I know are splitters, not lumpers, and by all means, do what makes you happy. And then the smooth flow topography inside the crater, which includes the faults. Okay, so that's your map. I didn't map over here because I don't have enough certainty and I'm weird about things like that. There is one unit I want to change, and that's this green unit in here, which is the smooth low. And I just want to add that the smooth low has normal faults in it. So contains graben. Just add that in there. That's fine to go back and do some revision. Right. Hope that helped you learn to map some normal fault tectonics on Mercury.